The sun, a natural, environmentally friendly, and almost inexhaustible source of energy. The total of all the solar radiation that reaches the Earth is thousands of times more than all of the energy we are currently consuming. The question is how to take advantage of it. Kasper Moth-Poulsen is on a quest to find new ways to store solar energy. And he wants to do this with molecules. The storage of solar energy is a major challenge, not least in the sunshine-poor parts of the planet. Traditional technology would use solar cells and batteries, but Kasper and his team convert the sun's energy into chemical energy, stored in specially designed molecules, in order to be able to use solar energy whenever and wherever one wants.
The goal is to develop a closed system that can absorb sunlight, store it as chemical energy, and release the energy on demand.
As a 19-year-old, Kasper came very close to being a medalist in the International Chemistry Olympiad in Montreal.
After high school, he continued his studies in chemistry at the University of Copenhagen and received a PhD in molecular electronics. A few years later, in sunny California as a postdoc at the University of California in Berkeley, he began working in the field of thermal energy storage.
I worked with a ruthenium-based molecular solar thermal energy system, and I learned how to work with this and how to develop molecules in this context. When I moved to Sweden, we continued with the molecular solar thermal energy storage, but we decided to explore a new type of molecules based on made out of carbon and hydrogen and nitrogen, which is supposedly to be much cheaper and more sustainable in the future.
Kasper brought the idea of storing solar energy in molecules to his own research team and began developing it.
When we started out with this, we had molecules that could sustain a small number of cycles. What we have done now is to develop more efficient molecules that can do this energy storage cycle multiple times without any degradation.
Now, this research is booming, and his group at Chalmers University in Gothenburg has grown to 15 people.
And here are different arms,
okay.
So we can change it. Yeah.
What we do is first we sit here and design and draw our molecule, the new target. Then we go into the lab and synthesize the molecule and see if it functions as well as we hope for.
In the lab, the molecules are later built through chemical reactions. Hopefully, this results in the creation of a next generation of molecules that are better at storing solar energy.
Noise here. This one is also an important part. This one is a calibrator. So with this we can calibrate the intensity of the sunlight. So if I put it here, or here, or here, then I can check the intensity of the sun spectrum.
To measure capability for storing solar energy, they begin with a very simple experiment, using tanning lamps to illuminate the liquid solution with the molecules. When the molecules are illuminated, they become isomers that can store solar energy. Isomers are molecules with the same chemical formula, but in a different arrangement than would normally be found. The solar energy is stored when double bonds are broken and single bonds are formed. To release the energy, a catalyst is added and the process is reversed.
So if we have a very promising molecule, then we have to scale up and make a larger quantity so that we can test it in a larger scale. We go to the outdoor test facility and test the function in a real device. One of the challenges here is to release the energy in an efficient way. In practice, maybe it cannot run so many cycles, or it doesn't store enough energy. So the difficulty is to get all the properties right in the same molecule.
The higher the temperature of the thermal energy we can get out of the molecules, the more applications can be envisioned. And the next step is within reach.
Some of the most efficient systems in the world right now are capable of heating something approximately 10 degrees. The molecules we have made now should in principle be able to heat something more than 100 degrees. So that is what we would like to show in the near future. We'll see how far we get.
The idea is to be able to reuse the same molecules again and again for many years in a closed system without the adverse environmental impacts of carbon dioxide emissions or chemical byproducts. It could be used, for example, to heat houses, in industrial applications, or for conversion to electricity.
So the dream is that in 10 or 15 years, we will have a molecular system that can absorb sunlight in an efficient way and release it as heat and generate a temperature gradient of several hundred degrees. That would be a sort of a universal solar energy battery that releases heat on demand.